Good evening, I guess morning over there. I decided I should record the last few introduction lectures before my login credentials timeout. I have 14 days that I can log in starting from when I was in DIA. Okay, so I'm going to continue with a discussion about safety in design. So we'll talk about safety load and resistance. I'm going to cast my iPad. So just a second. Here we go. And there we go. Okay, so we're going to talk about safety and the structural philosophy behind safety. So in this picture, you see this building, Bailey's Crossroads. Concrete was being placed way up on the 24th floor. And when you make a concrete building like this, you have to hold up the formwork. And usually you need 2 floors worth of strength to be able to hold up the green concrete. And so they were shoring from the 22nd to the 24th floor, and they removed the shoring from the 22nd floor too early. Things weren't cured enough. It started collapsing, and then it collapsed all the way down to the ground because one floor fell on the next, and it was 2 floors, and then once it started going, there was no way to stop it. This was in 1973 in Virginia, and 14 people were killed. Okay, so let's talk about loads. ASCE 7 is what governs the loads in the United States. And there are 2 kinds of loads. There's service loads for every day. We talked about limit states earlier. And then there's the ultimate loads, the factored loads. So these service loads are every day. And these ultimate loads are once in a lifetime and the lifetime of the building, and once in a lifetime worst case scenario. Okay, and the kinds of loads that go on buildings are dead loads, live loads, wind loads. Oh, I guess you could read that. Snow loads, earthquake. Doing a lot of that kind of work here in Japan. And these loads that are made by ASCE 7, okay, defined by ASCE 7, they get adopted into our local building code. And so, for example, in Laramie, our building code adopts ASCE 7, except we replace the ground snow load. I think it's supposed to be 20 in ASCE 7, and we say 30. And that's a variance from the ASCE 7. Okay, and then the kinds of loads we want to talk about are service or ultimate. Okay, so now let's talk about strength. So that's the load side of things, and now let's talk about the strength. So you make a beam and you make 100 of them, and then you break them. They're not all going to be the same strength, and so you're going to get some sort of distribution like this. Okay, and so here's a moment capacity of a beam, and the average strength, I don't know, it looks like it's about 47 maybe. There's 50 right there, so 47. Okay, the loads also have a distribution. Okay, so this is applied moment. So the strength was way out here, the average strength. And so most of our loads are below that. In fact, the average load looks to be about, I don't know, 23 foot kips, okay? So this is the whole goal of structural engineering. You want to make the beam bigger than the loads, okay? And so safety, let's define safety as a difference between the strength minus the loads, S minus Q. Okay, so here's the distribution of the strength and the distribution of the loads. And then this area here represents all the time that the loads are greater than the strength. Okay, so if you subtract the strength minus the loads, okay, and then you plot that distribution, it's here. And so anything, okay, this side of 0, that's unsafe, right? If it's negative, that means the applied moment was greater than the strength. Okay, so make it negative. And this is safe. Now it's impossible to make that go away. This will always be there. Okay, what we want to do is decide on how small we want that to be. Okay, so this is what we're going to do in our code. This is a strength. We want it to be greater than the loads. Okay, and both of these things vary, right? The strength varies. It might not quite be as strong as you want. The concrete could be bad. The steel could be misplaced. And the loads can vary. Like all of a sudden, you're doing something like, oh, let's see how many people we can put in a room. And then the load gets real high. Okay, so the basic concept, okay, that we have is we want the strength, but we're going to reduce it, okay, because we can't count on having a full strength, has to be greater than the loads, and we're going to factor those up for a worst case scenario. And this is the equation we'll use. Phi mn is greater than mu, and of course, phi is less than 1. Okay, I want to talk about these two letters, n and u. Okay, so u. We say ultimate load, but what I want you to think of is unusual. U stands for the most unusual load. Okay, we factor those loads up. Okay, so we increase them to represent the worst case scenario. And so, for example, the most common combination is 1.2 dead and 1.6 live. There are lots of other combinations. You can find them in any textbook. You learn about them in your structural analysis course. And of course, I'll have them on upcoming slides. Now, N, so we're talking about the two letters, remember? N and U. So U stands for unusual. N stands for nominal. Okay, and so nominal, okay, if you look it up in a dictionary, nominal means in name only. So, for example, we designed the beam and it can hold, according to our calculations, it can hold 100 foot kips. But that's in name only. How much it really holds might be less. Okay, so N is nominal. So you can have a nominal moment strength, a nominal shear strength, a nominal torsional strength, okay, nominal axial strength. Okay, these are nominal in name only, or you can think theoretical strengths. So to get the reliable strength, because something bad's going to happen, you reduce the nominal strength with a reduction factor, phi, and phi is less than 1. How much less than 1 depends on the uncertainty of the strength. Different strengths have different reduction factors. The moment reduction factor is not as much as the shear reduction factor because we understand moment better. Okay, now those load combinations we are talking about. Okay, table 1.2L for load factors. Okay, here they all are. You can download these slides. You can find these in any book. You can probably just Google them anywhere. but these are all the combinations that there are. One thing I want to point out though here is 1.0 earthquake. The earthquake loads are already factored up. Here's another weird one. You reduce the live roof load or the snow load because sometimes they help you. And in this case here, the wind can cause suction on your roof and lift your roof up. And so the snow, live roof, or rain is helping you because it's holding the roof down. So you reduce it in the worst case scenario. Okay, and then here are those strength reduction factors. So if concrete member is controlled by tension, it's governed by the steel because remember the concrete doesn't have tension strength or it's very low. So the tension strength comes from the steel. So typically tension controlled structures or sections are governed by steel, and steel is much more reliable than concrete. So you have a very high reduction factor. It's just barely less than 1. If it's compression controlled, look, you can only count on 70%. If it has spiral reinforcement, we'll talk about what that means, but typically it's only 65% you can count on. Shear, 75% you can rely on. Bearing, 65%. Post-tension anchorage zones. This would be in the next class, ARECE 50 to 60. And it just so happens while I've been here in Japan, I've been emailing back and forth with the professor who is going to be relocating to Wyoming in retirement during the falls. He'll teach pre-stressed concrete. His name's Trey Hamilton, and that'll be a treat to take a class from him. But anyway, I'm in post-tension anchorage zones, which is a pre-stressed topic. You can only reduce 15%. And strut and tie models, we'll talk about this maybe. This is for shear. Okay, and those have a 75% reliability, or you reduce 25%, similar to this, right? Because these are also shear. Okay, a little historical note. These things were different before 2002. So these are the ones I just described to you. And this was pre-2002, okay, there. And you would have higher loads, okay, but you would also have higher reliability. Now, this doesn't quite make sense, right? The loads are the loads. And I think what happened, and I'm pretty sure this is true, these look bad. See how low these numbers are? And then if you're brand new to strength design, you're going like, what? I have to throw away 25% or 30% or even 35% of my strength. I can't count on it. And these numbers are lower than steel. And so it makes concrete look bad. And so you could artificially increase them, but you would also have to increase the loads and it would all wash out. And concrete became load resistant factor design first before steel. And so they could do whatever they wanted. And then when steel came in, steel used the real numbers, 1.2, 1.6. And so in the old days, you would have to do a structural analysis for concrete with these numbers and redo the structural analysis with these numbers for steel. It didn't make any sense. And so finally in 2002, because these numbers here, I think are from 1973 on, or 71 or 73. And in 2002, the concrete people fessed up, changed it to what we have now with the real load factors and lower reduction factors. Okay, so that's that for safety, and we'll continue with other lectures. Okay, so I'm not sure what the next one is, so I'll end the meeting. Okay.